Well, good afternoon. My name is Joe Hewitt. We had a slight change from the conference presentation, but Gregory Nichols sends his regards. I'm with the Homeland Defense and Security Information Analysis Center. It's a bit of a mouthful, but we are a DoD chartered organization. We bring together the best and brightest scientists and engineers in industry, academia, and especially within DoD and other federal agencies, especially DOE as well. We bring them together to solve the government's toughest science and technology problems. We are a part of DTIC, the Defense Technical Information Center. So the work we're going to discuss today reflects a collaboration between Georgia Tech and their Athena lab in ECE and HDIAC. And just as it happens, I myself am a Georgia Tech grad, but I'll warn you, I'm not an engineer, much less an electrical engineer. I got a degree there in the history and policy of technology. So special applications indeed. So when it comes to energy use overall, the Department of Defense is the largest consumer worldwide. In fiscal year 2015, they spent $17 billion US on all primary and delivered energy. And that included about 5 billion gallons of motor gasoline, which is a volume that it's difficult to even contemplate. Today we're looking at energy on a small scale, the individual warfighter. And now that's kind of a term of art. It includes soldiers, Marines, and sailors. So we use warfighter to include all service branches. So we're looking at the small scale, the individual warfighter, and especially the battery weight. So to reduce that weight, the Department of Defense is very interested in what's known as energy harvesting. Essentially, all energy, of course, is us harvesting it, even burning, say, natural gas. But here we're looking mostly at harvesting energy from the immediate environment, and mostly in a passive way. So recent technologies developed in the past 10 or 15 years, especially 3D printing, additive printing, have made it possible to integrate multiple energy harvesting systems into a single unit, most likely used in a uniform combat suit. So we're going to review two recent pieces of work, in particular, a hybrid energy harvesting system of radio frequency and solar energy, and then a second one that includes solar energy and that should be triboelectric. So it's appropriate that the benevolent organizers of the conference gave us these as a party gift, because it's always a pain, of course, to run out of battery life on the go. But the warfighter cannot run out of power at all. So they usually carry up to 100 to 120 pounds of electrical related equipment alone, which is an immense amount, and is really only projected to increase as warfighters take on additional electronic equipment, sensors, and other command and control pieces. So energy harvesting is of great interest to DoD, naturally. You can either allow the fighter to have an extended range on the same size and weight of battery that they use currently, or to reduce that battery weight, give them the same range with less weight on the battery. In general, more power that's available to the warfighter on his or her feet means fewer supply trips, less equipment, less energy waste, and generally more secure operation. So in general, we harvest energy from two overall sources: ambient energy, like solar power, which is just there, or metabolic energy. So our keynote speaker this morning, Matt Roberts, mentioned that humans are generally powered by burritos, which is true, and I assume at least a few of you are as well today after lunch. So it's not that we waste caloric energy, but that it is wasted as well, and we can reclaim or capture some of that energy. The caloric energy generally goes in heat, body heat, but also movement as well. So we've got 4 different energy harvesting methods on the screen, and each of them provides unique opportunities, but also fairly significant limitations. Solar power, of course, is the most powerful ambient energy there is, but unfortunately it's only there half the day, and oftentimes obscured by clouds and the like. And as you might imagine, military planners often prefer to operate under the cover of darkness, so that makes solar power alone insufficient. But when potentially combined with at least one or potentially all of the other forms, we can yield a usable amount of electricity. So for example, radio frequency or electronic magnetic waves, although they have a low power density, they're almost entirely ubiquitous, especially near urban or settled areas. And with a high gain antenna, you may not collect a whole lot of power. It may be on the level of microwatts, but it will always be there. So the idea is, how do we combine multiple methods into a multi-spectrum or hybrid energy harvesting system or suit, most likely? Here we have a block diagram of just one such system. And we are focused today on the left 2 boxes, essentially the generation or the capture of energy and the power management of it. Whether we're taking that power directly to an application or storing it in some manner. So this leads to a couple of technical questions. What is the proper architecture of these circuits and the overall system, depending on how many ambient energy sources they are combining? What are the chances for interference between or among the subsystems? And how can we optimize them? How do we make a hybrid energy harvesting system produce more power than just the sum of its constituent parts? And does that involve, as is displayed here, the use of other unique pieces of equipment like a power management unit? So to this end, earlier this year, a team from Georgia Tech combined a solar cell and a RF antenna into a single hybrid system. Now, they were looking specifically at powering a small sensor and a 2.4 gigahertz dual port antenna. They essentially wanted to create a standalone unit that could receive and transmit information, but remain powered at all times, even at night. So this work has been done before, similar work has been done before, but this team, their results were far more promising for DoD applications. Their system was far more sensitive than previous work, and they were able to show that the 2 energy harvesting subsystems did not interfere, and in the way that they designed them, and here's a block diagram of their design. This design plus the power management unit, the PMU, resulted in 40% higher energy than would otherwise be created by the RF system and the solar system side by side. It goes for saying that what they actually constructed was a small physical box. The antenna was additively printed, about 2 inches tall, and the solar cell was on the top. So not quite to the point of strapping that on your back in the form of a jacket, but it's close. Even closer, in 2016, a different team at Georgia Tech, in collaboration with 2 Chinese universities in Beijing, they built a hybrid, usable textile that combines solar power through photovoltaic fibers and triboelectric fibers as well. So this work resulted in a 2-scale textile that was thin and pliable enough for use and could withstand multiple deformations, and could even power a cell phone. So essentially, it's enough energy as this here. They tested this fabric in a couple of different ways, which proved especially interesting. They fabricated the textile in 3 different weaves. A plain weave, a satin weave, and a twill weave. And to the dismay of college professors everywhere, the twill was least effective. Plain was most, when both subjected to solar power and to standardized deformation of the textile. They then also tested this textile in a different way, kind of a macro scale option. Rather than weaving, intertwining the 2 different types together closely, they, on a macro scale, put them in mosaic patterns and then also in strip patterns to see which would be most effective. There again, the plain weave and mosaic was most successful. But I think probably most notable about this piece of research is that they also discovered that the differences between those weaves were quite limited, quite small. Far more important to the energy production was the mode of electrical connection within the system. It significantly altered the system's output. So when they connected the 2 subsystems in series, the triboelectric system completely overwhelmed the solar power. When they then put it in parallel and received the opposite outcome, the solar power made the triboelectricity completely ineffective. So only when regulated by unidirectional blocking diodes did the 2 systems begin to produce more power than only the sum of their parts, thus yielding more energy. Also notable in this work is that they were able to manufacture this textile in a way that would allow for industrial scale production. That is certainly key when we're talking about moving research from the lab to the battlefield. They also found that the textile gave them a wide array of tunable options, depending both on the weave and the structure of the weave. They could maximize, say, solar power gain versus triboelectricity. Say, if you were operating in a particularly sunny area, in which laying out the textile or putting it on top of a tent would be most effective. You could alternatively reduce the solar power's impact on the fabric in an area where the light was diffuse or where the warfighter would be continually manipulating and deforming the textile, whether it was a shirt or a blanket. So both of the systems discussed today demonstrate that multiple energy harvesting sources can be combined in close quarters with minimal to no interference, maximizing overall energy gain. And finding ways to advance, optimize, minimize, and eventually ruggedize these systems will undoubtedly be a top priority for the Department of Defense for decades to come. So thank you.